who signed up won't be able to make it today. So it will be only me and one other person. So yeah, just wanted to clarify that. Okay, so today's session we're going to talk about linear models, and I think every machine learning course is has this section because it's like super important, and also like it's applied everywhere. You will see like everywhere linear models are being applied. There are different types, of course, but depending on the problem, like linear models are super prevalent in the domain of machine learning. So yes, my name is Rohan, and a bit about myself. Um, just a second. Yeah. Okay. So I'm a master's student at the UFA, University of Alberta, here in Edmonton, and I study computing science. I'm in my second year, and my research primarily focuses on machine learning and neuroscience, and like the intersection between the two. And I try to like implement machine learning models and uh, understand how the human brain processes language. And I primarily use like and work on like brain imaging data, for example, EEG, MEG, fMRI, and all that stuff. Okay, and I am a volunteer at GTG Edmonton, and I work there as like a technical speaker and one of the organizers. And when I'm not like studying or doing research, you'll like find me usually in the gym. I do love bodybuilding, and I try to find a lot of recipes on the internet and cook them, but it doesn't always turn out great. So yeah, that's a bit about me. So after this, I'm going to like dive right into the content. So just as to like save time. So linear models, like any other machine learning model, focuses on one part of or one category of machine learning problems, that is a prediction problem or supervised learning. So given an input X, you have some data, you try to predict some output Y. And just like this equation here, Y equals Fx, you can like um, create an association and establish a relationship between the input and the output. And F can be linear or non-linear. It doesn't have to be like uh, linear. It can be like non-linear. So we will see like later how the input data can be modified to like incorporate non-linearity, even though the machine learning model is linear. Today we are going to only talk about like linear models, but later other models. Neural networks is like a very easy example of a non-linear model. X is usually a matrix, but in this case, I'll like simplify it and try to make you understand how from the like ground up, from using one single value in X, you can like have an output Y. And one more thing I should mention before like I move on. This is like an overview of the Andrew NG lecture that I posted in the Slack. Yeah, so this is like just like a recap of that. So if you have watched it, it's good. You'll get a good recap. If you haven't, you'll get a recap anyway. Okay. And Y is usually a set of values. So let's say you have like 10 inputs, you will have like corresponding 10 values. So you're predicting Y from X. Fine. And so you might have seen this picture in many places if you're like exposed to machine learning for quite some time now. So what you have here is two axes, X and Y. And if you remember from the last slide, that is Y equals Fx. X is on the X-axis. You apply some function on it and you get a corresponding Y value on the Y-axis. And this line here is just a approximation of how well this line models this scattering of these data points. Okay, so this is a scatter plot and this is like a line. And so if you just remove the line, you can see that there's like a linear relationship between the input and the output. Okay, and this line just like represents that. Now the question is, how do you establish a relationship between the input X and the output Y? So the way we do that is using a transformation. In this case, it is represented by theta, but in many places and also in the notebooks, you will see that theta is just a symbol and it's like replaced by W. So just keep that in mind. So yeah, any kind of transformation that you apply on any data gives you something else, and that something else is the output. And the task of modeling or any kind of modeling problem is to find what transformation should you apply to get the output from the input. Okay. So the goal is to find theta, which is the transformation. And our hypothesis is that there is a relationship between the input and the output. If there isn't a relationship, I mean, there's like tons of tests that you can do. One of my favorite is the permutation test. You can look it up online. I'm not going to discuss it here, but the hypothesis we make before we dive into linear modeling is there is a relationship between the input and the output. Okay, and that relationship is established by the transformation matrix theta. Now, in this example, I'll consider x as a single valued variable and y as a single valued output, and theta also as a single valued parameter. Okay, and so x, I'm like just representing capital X by small x because it's one variable, and since I only have like one variable, I only need one parameter, so I'm just going to represent that with theta 1. Okay, and thetas are called parameters, as I said earlier, and different theta gives you like different hypotheses. So what I mean by that, if you change the transformation value, you will get a different relationship between the input and the output. So for example, consider like x has a value of 2. If you set theta equal to 2, you will get y equals 4. If you set theta equals 1.4, you will get like something 2 times 1.4. If you get like theta equals 0.5, you'll get 1 as output and y. So hypotheses differ based on the value of theta, but the model remains the same. Okay. Now let's like move on to the cost function. So what does the cost function is? What is the cost function and why do we need it? So if you go to the previous slide, our goal is to find theta. But how do you find theta? What's the best theta that you can get? How do you measure the bestness, even though that's not a word, but you get the idea. How do you measure how good our theta is? And that's where the cost function comes in. Cost function is like a way to measure how good our prediction is. So if you look on the right here, I'm sure you can see my pointer. So MSE, or the mean squared error, is, if you like just ignore this summation term and 1 by 2m, I'll tell you what that is later. It's like a squared difference between like y hat, which is like the predicted value, and y. In this case, it's like there's like a superscript I representing that there can be more than one y values. But for simplicity, if you have like one example, one input and one output, you can like remove the I. So if this is 0, then we have like a perfect prediction. And that's what we ideally want, even though it's not possible and sometimes undesirable because of overfitting and stuff, which we will dive into later. But the smaller the difference, the better our model or better our theta value is. Okay. So y hat, um, I should have like made this like y hat, but like the y hat is the prediction. And after you like find theta, or while in the process of finding theta, you make predictions and calculate the difference, and you try to minimize the difference between y hat and y. Okay. Now, I guess I should also mention we do add like a bias term. It's called the bias term, called theta 0. And this is like the intercept of the at the y-axis. So if you think this line, if you like remove this theta 0, this line will like pass through origin. If you like add theta 0, you can like move this line up and down. So that's the bias. Okay. So imagine like if you don't put the bias term, and this line is like passing through the origin. It will be like in aligned with the slope of the scattered data points, but it will not exactly like overlap. So that's where the bias term comes in. So yeah, MSE is called the mean squared error, and it's like the summation over all the squared differences for all the outputs. And it's represented usually by J, theta 0, theta 1, up to theta n if there are like more features. So it will have like more thetas. J is just a cost function. It's like convention. So there's no really solid reason behind that. And the goal is to minimize the cost function. So our initial goal was to find theta, which uh, requires an auxiliary task, that is to minimize the cost function. And if we minimize the cost function, you can like visualize how we can get the optimal parameters, right? So if we have like a very good or very small difference between the in predicted and the true value, which is like the MSE, the mean squared error, we can see that how the parameters or the theta values are good enough. Okay, fine. So let's like now visualize the cost function. So how do we like uh, how can we like imagine how does it work? Just to, this is just to get an intuition. It's certainly not necessary to like implement the models, but just gives you like a deeper understanding of why the cost function is important. Okay, for linear models, um, our cost function is like convex because um, uh, the parameters actually have like a nice kind of convex property, and so it's like the algorithm that we'll discuss later, which is called gradient descent, works nicely. But it might also be possible that we'll just look into it later. I think it's a couple of slides from now, that this cost function cannot be or won't be like convex or just like a bowl. It won't be like that. It will be like jaggery and all that stuff. Okay, so um, it's a 3D plot here, and in one of the axes you have theta 1, and in the other you have theta 0. And our goal is to get to the bottom of this bowl, okay, of this like 3D curve. So you can like start anywhere on this plot, and you can slowly move to the center, which is like the bottom of this blue area. Okay, and how do we do that? We try to minimize the cost function, and if you like reach the bottom, we get like a good approximation of theta, and you use the gradient descent algorithm to do that. And gradient descent basically means you use the gradient or the slope at any point to decide which direction you will take a step. So that's called gradient descent, because you're descending to the minimum and you're using the gradient at any point in time to decide which direction you should go. Okay, so gradient descent. And as I said like earlier, the cost function can also be like non-convex. So this is like a non-convex cost function. And this is like one of the problems that machine learning researchers and engineers like face almost every day. Because if the in the previous case we had like a one global minimum, right? This is called a global minimum because there's like one single value that um, is very close to the true parameter values. But if there are like different minimums or minimas, so these are called like local minima. This is one of the local minima. This is another one. So what happens if you get stuck in a local minima? So this is where one of the problems actually, one of the core problems of machine learning actually comes into play, because if you don't if you don't reach the global minima, you truly don't have the exact or truly approximate or approximately close enough to the true values of theta, right? So the way we solve that is another technique that we'll look into the notebook. It's called cross-validation. But yeah, just to put it out there, um, cost functions cannot be or won't be always convex. A linear regression it is, but almost Well, like in case of neural networks, it's certainly not. Okay, so let's like talk about this picture just one more minute. So let's say given two starting points, if you start from this point on the right, it's possible that the steps that you take, depending on the slope, will um, make you reach this minimum. This may or may not be the optimal solution, and this is called one of the local minimums. If you start from this point on the left, you might reach here. Okay, this may or may not be the global minimum, but it is certainly one local minimum. And a local minimum can be a global minimum. So just make sure you understand that. Okay. Now here's the gradient descent algorithm and how it actually works. You can like use this formulation to implement in Python and it will work just fine. So the algorithm is like repeat until convergence. So you have like theta j, it can be theta 0 or theta 1 up to theta k. And you update your theta or you take a step in one direction based on the slope of the cost function times some alpha. Alpha is like how long this step should be or the step size. And this derivative of j theta, if you're familiar with calculus, it's just the slope. Okay. Yeah, so alpha is the learning rate or the step size, and j theta is the cost function. So for two parameters, theta 0 and theta 1, you have this like four steps here that you can like just implement, which is nothing but this equation expanded. Okay, so theta 0 will be like if you take the derivative of j theta with respect to 0 and multiplied by alpha, you like um, update theta 0 here, and the same goes for theta 1, but make sure you take the derivative of j theta with respect to theta 1. So if you have taken like the derivative of j theta with respect to theta 0, theta 1 will be treated as a constant. If you're taking the derivative with respect to theta 1, theta 0 will be treated as a constant. Okay, and you can like go to this link. Even though I feel that this is like a pretty good explanation, but if you want to like learn more, you can like go to this link. Try to post the slides on Slack later. Okay, so types of gradient descent. So what we looked at was stochastic gradient descent, or like what you do is you read each sample in a set of samples. So let's say there are like 10 samples. After reading the first sample, you update the weights. After reading the samples, second sample, you update the weights. After reading the third sample, you update the weights till you reach the end. There are two more variations called the batch and the mini batch. So what happens in batch, you go through all the samples and then update the weights at once at the end of reading all the 10 samples. In mini batch, what happens is you decide before actually going through the algorithm how many um, what's the size of the batch that you want to go through before updating the weights. So let's say there are 10 samples and you decide the mini batch size is 3. So after 3 samples, you like go through, you update the weights once, and the next 3 samples, you update the weights again, and so on and so forth. And obviously, if you like set the mini batch size to like the number of samples, it becomes batch gradient descent. And if you set the mini batch size as 1, it becomes stochastic gradient descent, which is like evident from like the categories of gradient descent. Okay, so I gave you an example where we consider the input x as only a single variable or like a single feature or one value. What happens if we consider the x input as a set of many values? So let's say there are 10 samples and each sample has like 5 values. So you can imagine in your head like a matrix of size 10 rows and 5 columns, because each row will have like 5 values. So you have like a matrix of size 10 cross 5. In this case, I've written it as n, but n can be anything, any integer, positive integer. And depending on the values of x, how many columns are there or how many features are there, that is the number of theta parameters. Okay, so let's say you have like 5 columns, you will have 5 theta parameters, excluding theta 0 and x 0. Okay, so just wanted to make sure that's clear, because that's like a bias term that we add to the model. It's not included in the data. When we have like um, these matrices of data, we can like leverage the power of linear algebra and make our lives easier because it's like super cool. And you will see that in the notebooks how linear algebra is like used behind the scenes to like just solve everything. And this is my handwriting, which is not so good. But what I want to like display here is essentially, if we want to use like linear algebra, you can actually expand that and unroll the matrices to get the first equation. So imagine like you just omit from like theta 2x2 up till like theta n xn and like just focus on this. We saw this like a couple of slides ago, theta 0 plus theta 1x1, which is nothing but if our input has only one variable. If it has like more variables, if you recall from the previous slide, you can just add theta 2 to x2, theta 3 to x3, and so on and so forth. And these 2x and theta matrices are just a way of representing. It's like nothing fancy. Um, and you can like have x1, x2, x3 up to xn, and x0 is the bias term. And theta is correspondingly theta 0, theta 1, theta 2 up till theta n. And theta is multiplied with x0 to like just get this equation. And all of these like values belong to set of real numbers, same for the theta. Now, if you want to represent this equation in a matrix format, now if you like code this, you can imagine how much time it will like take you to actually code this. Like if you have like, let's say 1,000 features, what will you do? Will you actually do theta 1 plus x1, theta 2 plus x2 up till like theta 1,000 plus x 1,000? You won't do that. It's like, it's not feasible. It's like stupid. So what we do is get the matrix format and just do a matrix multiplication. And that's what I've done here. So theta transpose time x. Okay. So if you like transpose this and if you like multiply the transpose of this with x, you will get one single value, which is nothing but y. Yeah, and also hx of theta is, sorry, h theta x is y. Okay, because it's like a prediction. Okay, so here's a question to you guys. You can like type it in the chat or maybe unmute yourself. It's up to you. What is the value of x0? It's a simple question, but just to get the audience engagement. So yeah, take like 1 minute and answer that question.
1.
Sure, yeah. So x0 has the value of 1. And do you know why?
I guess that is because we need actually to have the same dimension of the other x's just to get the proper multiplication. I mean,
Yes, I mean, yeah, that's a good enough explanation. But the key point here was that bias. So theta 0 and x0 is not included in the data, and the user who is implementing the machine learning model is including that as a bias term. So that's like the point of x0. But yeah, just a simple question, nothing important. And yeah, this is like the cost function for multiple variables. It's the same as that of theta 0 and theta 1. And you see that y cap is replaced with h theta x, and that signifies that h theta x and y hat are equivalent. They are the same thing. And if you have multiple parameters, you just take the summation or h theta x from the previous slide, this one or this one, get the y hat, subtract y or the true value from y hat and square that and do the summation across all these samples. Here m is the number of samples. Okay, and there is like a 2 here because we will take the derivative. If you remember like how gradient descent works, we take like the derivative here. And if you take the derivative of this one, the 2 comes here and the 2 and 2 cancel each other out. That makes our lives easier. So that's why the 2 is there. It's nothing fancy. And this algorithm is the same thing. So as I showed you earlier, gradient descent with theta 0 and theta 1, you have many features and it's the same thing. Just one thing to note here is the parameter with which you take the derivative against. So here you take the derivative with respect to theta j, and that's the parameter you're updating. Don't like, if you have like theta j, don't take the derivative with respect to like theta 0 or something. It's incorrect, okay? Now, so I showed you like the gradient descent algorithm, and if you understand that correctly, it should be clear to you that's an iterative algorithm. So you do many iterations before you reach the a good value of theta, or good enough according to the user. So here's a solution that is like, it's called the normal solution or the closed form solution. Why is it called that? We like look into the notebooks and get more understanding of it. But this solution is good when you don't want to do iterations, okay? You don't want to do like step size selections because that's one other problem, which is like a very important problem. If you like make the step size too low, it will like take a very, very, very long time to converge. If you like set the step size very high, it will like oscillate between one point. So it's like another problem. And we'll actually look into some examples in the notebook itself. Okay, if you have like one single value in the input, which is never the case, you can use gradient descent, okay? And sometimes we also use gradient descent in production and like in research, but I personally don't use because I know that it's not like this closed form solution is way quicker. So one of the times when you can use the closed form solution is when the input has many features. So let's say it has like, um, you have like, you in your data set, you have like 1,000 samples, but you have like 10,000 features. You can use that. Um, but if like the features are like too high, again, uh, you can see why this is like very computation intensive, right? So if it's not clear, I'll explain it to you why it's like so bad if you have like very large set of features. Even though like modern computers, they can process it really quickly, but still it's like very expensive. So you have the value of theta here, and theta again is a set of theta 0 to theta n. You have the input x, you take the transpose, and you multiply it with x itself, so x transpose x. You take the inverse of it, which is another like expensive operation. You multiply that with x transpose, and finally you multiply it by the true value y, and you get like a closed form solution theta. So you can do this. Uh, it works well generally. But what if the determinant of x transpose x is 0? In that case, you cannot like find the inverse, okay? Because you cannot find the inverse of a determinant that is like 0. So yeah. So in cases like those, this actually fails. And yeah, so that's like one of the drawbacks of closed form solution. But you can solve this with regularization. That is one thing um, which I'll talk about later, and also Saurav will talk about in one of his notebooks. But just FYI, you can solve this using regularization, which I think is pretty cool. Okay, I think that's the end of the presentation, at least this one. Yeah. So now we are running okay on time, I guess. Yes. So I guess I'll now move on to the Jupyter notebook. So before moving on, any questions?
Yeah, Rohan, there are some questions in the chat, and Jean will summarize those questions and ask you here probably.
Okay.
I guess there's one question regarding the I'm just scrolling down the question. So what's the difference or the advantage and disadvantage of each gradient descent types like stochastic, batch, and mini batch?
Right. So I guess one of the advantage of stochastic gradient descent is like you can actually see your weights being updated in real time because it's like so quick because they're updating the weights after every samples after going through every sample. So this actually gives you like one advantage that you can actually see that your weights are being updated correctly and there it's not going the other direction of which you want it to go. So if there are like some problems that are in your algorithm, you can easily stop the process and debug it. So that's one like very good advantage of stochastic gradient descent. One advantage of batch gradient descent is um, each time you update the weights, you know if your algorithm is working correctly, that is. Each time you update the weights, because you have gone through all the samples, the number of iterations that you need to get to a like the close approximate solution, it will be like very less, and the update will be like very smooth. So if you like plot the theta values over time, you will see like a very smooth curve going from top to the close, the actual theta value or the close enough theta value. One disadvantage of batch is that it's like computationally expensive because you have to go through all the samples and like um, just calculate the gradient across all of them and then like update the weights. So that's, and like mini batch is like a trade-off between stochastic and batch. So you have like good enough um, approximation, but you also don't want to spend enough that much computation. So that's like one of the like a middle ground between stochastic and mini batch. I think I also didn't mention the disadvantage of stochastic. So one disadvantage of stochastic is that if you like plot the theta values, you will see like a very spiky line like going up and going down. So jaggery. You need like many iterations to like actually reach the true or the close enough theta value to the true theta value. So I hope that answers your question. What are the other questions? Um, so what is the difference between cost function and loss function? Is the same thing. Um, I know like I personally regard them as the same thing because they are, but I've seen like in many places the terms are like interchanged. Um, yeah, it's actually the same thing. Loss function is like a more general term for any specific cost function because if you have like if you let's say consider logistic regression, then the cost function will be different, but the loss is called the logistic loss. So it's like I think it like talks about the same thing, but depends on the problem itself. So, but you can just like think of it as the same thing. It's not a big deal. Why is the intercept considered a bias term? Hmm. So think of y equals mx plus c, which is nothing but the equation of a straight line, right? If you remove c, what will happen? The line will pass through the origin. So c is called the intercept, which like moves the line up and down in the y-axis, and that's why it's called um, the intercept. But why is it called the bias term? I think it will be more relevant to you if I just move over to the notebook and talk about it. Because in like there's like a bias variance trade-off, and we will like dive into the math a lot, and there will be a lot of questions, and I won't be able to answer all of them, but yeah. It's called the intercept because it follows from like y equals mx plus c. It helps to like move um, the y-axis up and down. Sorry, the line in the y-axis. Yes, I will provide the slides after, yes.
Yeah, thanks, Ruhan. I think you've pretty much answered all the questions, and we can save
Cool.
some
Okay,
of the other questions after the notebook.
cool. Fine. So I guess I'll move over to the notebook. Where is it? Yeah. Can you see the notebook?
Yes, we can.
Yes, we can see
Okay,
it.
okay. Yeah, good. Fine. Okay. So we talked about linear regression gradient descent, the closed form solution, the cost function, the loss function, whatever you want to call it. And yeah, now what we're going to do is we're going to move on to some code. But before that, let's get into more mathy. Um, so linear regression, linear classification and regression. Okay. Part one is the ordinary least squares regression. It's like a variant of gradient descent. And we actually talked about it. So if I scroll down, you will see like this equation is the same here. So, and also I think I mentioned this earlier, but from now on, replace theta with W. So whatever you saw in the presentation, just replace that with W. I kept the W as theta in the presentation because I wanted to like make it like consistent with the Andrew Ng lectures, but yeah, it's the same thing. Okay. So in this notebook, what happens is basically there's like a lot of explanation on why things are the way they are, and they also like give you mathematical explanations. I'll try to keep it as high level as possible because I'm short on time. Okay, so you saw this from the presentation, right? Y equals x w or theta, but there is one other term added here, which is the error. And this error is like this is like this captures that we won't be able to get an exact relationship between the input and the output. If we are using an approximation like gradient descent, we will never get like a true or exactly the same value as the true W or the true Y. Okay, so that's this error and what it represents. And this can be like of very many factors like choosing hyperparameters, which we'll talk about it later. Errors in observation. So let's say you collect the data from somewhere, there's an error in the data collection, human errors, and this epsilon term basically encapsulates all of those. Okay. Sorry, but where is the notebook? The notebook should be on the GitHub, I guess. Yeah, I think one of the organizers can post that in the chat. Okay. So moving on. This is nothing but um, this equation right here is nothing but this one, but expanded. This is like the matrix for multiplication format. This is like the summation format, and matrix multiplication is nothing but summation. So yeah, it's the same thing. If you don't understand this, like just take like some time to go through this. Okay, and it should be like really intuitive from here to this to this. Yeah. Okay. And if that's clear, I'll like move on to some derivations. Okay. So what we are doing now is going to the derivation or mathematical derivation of ordinary least squares regression. Okay. And I showed you in the presentation this equation, but I didn't give you the derivation. So That's what we are going to look at right now. So what we want to find in the end is W, and what we want to find is the expected value of the W, and we want to make it as close to the true value of W, which exists, but we want to find it, okay? And it all goes back to the hypothesis that there is a linear relationship between the input and the output. If there is a true W. We want to approximate it using either gradient descent or the closed form solution. Okay. Here we are looking at the closed form solution. Now, here the expected value of the W that we are trying to approximate will be equal to the true W. And if this happens, it's called the unbiased estimator, okay, or unbiased W. So the expectation is equal to the real but unknown value of the estimated parameter. Fine. And so what we have here, if you remember from the presentation, is the loss function. Now, one thing to note here is obviously y hat and y is interchanged. The positions are interchanged, but that doesn't matter because it's squared and it's the same thing. Okay. And one more change here is instead of m, we have n. In the Andrew Ng lectures, Andrew Ng like he likes to set the number of examples as m and features as n, but mostly or like majority of the tutorials online will give you like the number of samples as n or number of observations as n and the number of features as m. Just kind of swap it. So that's the only difference, but it shouldn't be big of a deal. Okay, so we have the loss function, okay, and you can rewrite this loss function like this, which is nothing but the square and the Frobenius norm or the L2 norm. You can like Google this. And if you want to like expand this, you can like also write it in this way. Okay. Now, if you remember from gradient descent, we take the derivative of the loss function with respect to theta j. In this case, since theta is w and w is like a set of many w's, so w0 to w n, it's represented by a bolded w, just to like show that it's like a set of many values. And what has been done here is basically the derivative of this has been taken. Okay, so we take the derivative of the loss function with respect to w, we get this. You can like do this if you want to like actually verify this by yourself. And if you simplify this, you will get this, okay? Now, if we go back a bit and we see that we want the expected value of wi, the unknown w, to be equal to the true w, we want the derivative equal to 0. So the loss or the difference between prediction and the true value should be 0, right? So that's why we set it to 0. And we set this value to 0 as done here. And we simplify this. And if we like simplify it again, that's how we get W. So it's like a really simple like algebraic operations. But the important thing to note here is that how we are getting from this line to this line. So you can like do this by yourself in your free time. So the primary idea is you have the loss function, take the derivative, set to 0, get the values of the parameters. That is the only idea that is working here. Okay. And now moving on, I'll move on to the maximum likelihood estimation, which is like a probabilistic approach to this closed form solution. But yeah, it follows the same model and the form is the same. So here there's an example where there are like 400 people and they were like asked, do you remember the formula for methyl alcohol, which is like CH3OH? And out of that, 117 people remembered the formula and 283 did not, okay? So how do we model this? Since this is like a binary problem, and we only have like probability of 1 and 0, either the person remembered the formula or that person did not. And so we can like use this formulation, which is called the Bernoulli distribution, to like model the outcome of theta given the input. And x will be equal to 0 or 1. So either the person remembered the formula or did not. Okay, and theta is like the parameter, which is nothing but the distribution parameter of the Bernoulli distribution. Okay, so you can like Google up Bernoulli distribution real quick and see how it looks. So you will get an understanding of what the theta represents. Now, if we um, go to this line, what it represents is how many people actually remember the formula, which is like 117. So you multiply everything for each x value. So let's say person 1 had value of 1, person 2 had the value of 0. So if you add up, it adds up to 117. And 1 minus theta is how many people did not remember the formula, and that is like 283. So this is just replacing x and 1 minus x with like 117 and 283. Okay, and we take the log because like it's easier to do operations on the log. And if you like take log on a product, and so this pi sign, this capital Greek letter pi sign, represents product. If you take the log of a product, it changes to summation, so it makes our lives easier. So that's why we take log. And this will also be important for the logistic regression. So this is like a mathematical trickery going on. That's like really helpful. And this is like the loss function. So again, we take the derivative, we set it to 0, and that's what we get here. And you can like just simplify this to get the value of theta. So this is just another example where you like change the loss function, the cost function, whatever you want to call it, take the derivative, set to 0, and get the value of parameters, just like we did here. So we have the loss function, took the derivative, set to 0, got the value of w. In this case, the w is theta. I know it's like a lot of interchanging going on, but it's the same thing. Okay, it should be clear and like really easy to understand, but if you don't, post it in the Slack and I'll try to help. And yeah, again, the equation or the model or the form of the equation is the same. It's just you have like the prediction, you have some error, you get the output y, and yeah, that's it. Fine. Now, so this is like one extension of how you can think of the equation, this equation. So x times w plus epsilon. Epsilon is usually considered to be taken from a normal distribution. So if you see like the bell curve, it's like goes something like this. It's like a bell and it like tapers off in the end. So it's like a normal distribution. Okay, and the error is usually sampled from that distribution. And this is the reason why um, why so y as the label is also like um, some value from the normal distribution, because if you add something to a um, if you add a normal distribution to some value, the output will also be a normal distribution. So y and epsilon also are sampled from a normal distribution. I think this is one of the reasons it's called a normal form. Yeah. Anyways, so if you can rewrite this, just replace epsilon I with the normal distribution format, and you can like just shorten this to like represent the probability of y given x and w, right? So what is the probability of y being, let's say, 1 given input x and the parameters w? I know this like is like very high level, but I really encourage you to like go through this and go through each of the steps and make sure you get an intuitive understanding of it. Okay, so again, we have like the equation, we take the log and we try to take the derivative, set it to 0, and it's the same thing all over again, just another format. So I think I should also spend 1 minute or two here just to explain what's happening here because this might seem confusing. So we take the log of the probability of y given the inputs x and w, um, and you sample that from a normal distribution. We take the product of it because we are trying to find the probability or maximizing the probability. And if you want to like maximize the probability, we take the product. We take the log because it will make our lives easier and change the product to a summation. Okay. If we take the log and if we take the summation, what happens is the products become separate, they get added, and so we get like a division of these two terms. Okay. If you want to verify this, it's like really easy to do it. You just replace um, this equation here and you will get this. Trust me, you will get this. Okay. And our goal was to find W. And how do we do that? We take the derivative, we set it to 0, solve for W. And it's not being done here because this is like a general form for any kind of loss function that is being that is like specific to the problem. So here it's like it's written arg max of this probability. So this probability, whoops, yeah, this probability, and also it is like the log of that probability because we take the log. And if you like replace this value here, so that's what we get. And if this is a constant because your standard deviation for the normal distribution is constant, and pi is a constant, n is a constant, 2 is a constant, everything is a constant. So we just omit this and try to minimize this just for like mathematical simplicity. And it changes from arg max to arg min because you have like a minus sign here. So if you like remove the minus sign, it's just same as like minimizing the negative log likelihood. So that's what it is. So just change the minus sign and it changes arg max to arg min. So arg min, what it says is basically take the derivative and set it to 0. That's what arg min is. Okay. Now, one more thing, which is super important for any mathematical machine learning, is understanding what this error represents. Okay. So the error can be actually broken down into many errors, reducible and irreducible, which will have the derivation here. Okay, so we saw earlier that y equals fx plus some epsilon. Um, epsilon is from a normal distribution and y is also normally distributed. And the reason for that. So what we do here is we try to break down the error. So what is the expected error that we are trying to achieve? Okay, what is the expected W? And if we find the expected W, what will be the expected error? So expected error is nothing but, if you remember from the mean squared error, the loss function is true value minus a predicted value and its square. If you use the a minus b whole square formula, this is the expansion that you get. And this is like a simplistic or simplified version of the second line. So y square remains y square, f at x whole square remains, it changes to f at square. And fx is represented by f hat, so y times f hat. Okay, the same thing. Now this is an equation, not an equation, but like a property. Variance of any value or any variable is the expected value of that variable squared minus the mean squared. Okay, so expected of z is the mean, and if you square that, you'll get the variance of that variable or z. So same property is being applied on each of the terms in this equation. So first we look at expectation of y squared. So you have like, if you use this equation here, you get like sigma squared, which is like the variance, and the f squared, which is the true prediction, not the true prediction, but like the prediction without the error. and it's squared. The variance, if you like find the expectation of this one, you have, and you apply the properties, the same property, you have this one, and it's like just note here that expectation, sorry, variance of y is nothing but sigma squared, and expectation of y is like f. Okay, so it's just, that's why it's like sigma squared plus f squared. There's like a note here. Now coming to the last term, so expectation of y times f hat. So if we simplify this, you get this. You can like go through the steps. It's like really intuitive. And if you like bring it all together, so steps, this one, and this one, you get this. And if you like just rearrange the terms, you get three terms. So the first is the bias, the second is the variance, and somebody asked like, what is the uh, why is the bias called the intercept or something like that? So it's called the intercept because it like moves your predictions from the actual prediction. So let's say your actual prediction was like 5, but you add a bias term of like 2, so now your output is like 7. So, and this 2 bias is like added to every prediction. So that's how you like move your predictions up and down the y-axis. You have like the variance of, or how much your prediction varies from the true value, and you have this sigma squared, which is nothing but the irreducible error. And you cannot just like solve this. It's like it will be there no matter what you do. Okay, so if you use a machine learning model, you will never get an exactly um, equal to the true value of the parameters. You will get like very close to it, but not exactly, because of the sigma squared term. And that's why it's called the irreducible or the irremovable error, as shown here. So other explanation. So bias f, a bias of like f hat, is the average error for all sets of data. So imagine like um, you have like different subsets of data, and if you like get these scores on all the data, what's the average error? So that's the bias value. Variance is the error variability. So how much does the error vary from the true error if we like train and test on like different subsets of data? So you have like the average error, which is like the um, mean error, and variance is like if you train on, let's say, one set of data, how much the error from that training process differs from the mean error from the that is nothing but the bias term. And what we want is like a good enough balance between the bias and the variance. Okay, so this picture right here is like a very good visualization of what we desire but what we get. So ideally we want like low bias and low variance. So we want like very low error and very low deviation from the error, or like variability of the error in our model. And if that happens, we'll get like all the points centered at this like red um, circle. But what happens is this, not so extreme, but something like this. So you have like low bias, fine, but the if you like train on multiple subsets of one big data set, you will get like different errors that have like this almost the same variability from the mean error. So this is what happens usually in reality. We don't want this, like this is like very underfitted model. So it's called underfitting because our model does not have a good understanding of the data or the relationship between the input and the output. And this is certainly not desirable, even though like you have high bias, it's like far from the um, true parameter values. Your like predictions also like vary a lot. So this case and this case is undesirable. This is ideal, but this is what happens usually. Okay. So if this happens, you will get like 95 and above accuracy, but this is what happens when you get like, yeah, 80%, like 85% above accuracy, but your results are like statistically significant. You can do like If you have taken a course on statistics, there are like certain cases, like certain tests like t-test and McNemar's test and all that stuff you can like check, and you will see that your results are significant. But ideally, this is what we want, but we don't get. And in life also, what we want, we never get. So anyways, and this is what I was talking about when I said we want like a balance between the bias and the variance. Okay. So if we want to like, so if you go down this graph, this is like the total error, which is the summation bias, variance, and sigma squared. Obviously, there will be some error. This is like the irreducible error, and we want to minimize this. So we find the minimum of this total error curve, and we also see that there's like some um, compromise between the variance and the bias that which will always be there. You can like cannot just solve this. You can find an optimal point, um, but you will never get like this won't be like exactly close to zero. It will never happen like that. So this is like a curve between how variance increasing the variance like reduces the bias, and how reducing the bias, sorry, increases the variance. So, and yeah, reducing the variance increases the bias. Yeah. So this is like a good um, graphical understanding of how these things work. Slightly dependent on each other because they are part of one error term, but yeah, that's how it works. Now, in the presentation, I told you, and this is what I find like super interesting, that if the X transpose X inverse matrix is singular, or yeah, if you look at this equation right here, or it's like degenerate or the determinant is zero, if I remember correctly, the inverse does not exist. What if the inverse does not exist? How can we solve this? How can we find a closed form solution? And that's why um, all most of these scikit-learn packages implement a regularized form of the algorithm. So what is regularization? Even though like Saurav will go more into it, but I'll give you an overview of what it is. What we do is we add some term, which is known as like, or implemented as lambda times the weight matrices, um, and we add it to the our loss function. Okay, and what this does is in the X transpose X case, if you like again get the derivative of this and set it to zero as we did earlier, this is what you will finally obtain. And if you can imagine, let's say this X transpose X is singular, and if you add something to it, it will not be singular because those zero values will now have some values, right? So you can take the inverse of it. So now this works. So we have solved the problem of singular matrices. So that's where regularization comes in. But it has like one other added advantage, and you can like verify this by yourself. If you increase the value of this lambda, what will happen is that it will penalize the weights which are like very high in value. So if the weights are very high in value, it will make it closer to zero. I will actually post like a very good article from Towards Data Science in the Slack. It gives like a very good intuition of how regularization L1 and L2 works. Okay, but just to give you an overview, if you want, if you like, if you want to make the model simpler, you regularize so that some of the weights are set to not exactly zero, but very close to zero. And that's how like you prevent overfitting. So this is like one of the other advantages of regularization. And I use regularization all the time in my projects. And if you're doing like a machine learning project, if you're new to machine learning, if you're experienced, it shouldn't be like a new thing for you. But if you're new to it, I would like encourage always regularizing your models. So this is one picture that shows that how the weights actually vary. So on the x-axis you have one weight, so W0, and on the y-axis you have W1, or you can, if you want to like recall with the presentation, it's like theta 0 and theta 1. If you don't include regularization, this is the solution that that you will get, like the closed form solution. And if you like vary the, for a regularized solution, you can see this light blue line. If you vary the lambda value, which is this one, you get like um, different solutions here. Okay, so different lambda values will have like will give you like different values of W. So higher lambda value in this case um, represents like more closer to this 0, and like lower lambda values will have like more closer to the actual maximum likelihood solution. MAP stands for maximum A posteriori, something like that. It's nothing but the Emily solution, but with regularization. Okay, so that's the end of notebook 1. I'll look for any questions.
And hi, Rohan. I think we got 4 questions here.
Okay.
And after these questions, probably we can take a short break. So one question is from Connor Wald. He asks if overfitting a model is caused by low bias and high variance.
Uh-huh.
Um,
Okay.
If so, it very closely fits your training set that can produce bad results with new data.
That's actually exactly right. So if you train on a data set that is very noisy and you don't regularize, it will certainly be the case that your training error and your test error will be very different. I think we have a notebook on regularization where we actually plot the training and validation curve. So you'll be able to look at how those vary. But what happens is, if the training and the test data set are from different distributions or different sampled from different distributions of data. So let's say you're like sampling the training data set from a normal distribution. If you're like testing on a data set from, let's say, Poisson distribution. If you train on the training set, which is from a normal distribution, your parameters will be according to that normal distribution. And if you like test it on the test set, which from Poisson, it doesn't work. So you'll get like bad results.
Okay, I think this question is solved here. So the second question is from Daniel Matt. He asks if gradient descending or stochastic gradient descending is more commonly used these days.
So I wouldn't say like stochastic gradient descent is used very commonly, because we have enough computation power to at least do like mini batch. So there's no, and algorithms are just what I think, like algorithms are pretty robust here, and in the Python packages, it's like very, it's like reviewed by everyone. Everybody uses this, and like I don't see like any errors that you need to actually implement stochastic gradient descent to look at your theta values, make sure algorithm is working. So yeah, I would say like mini batch is the way to go.
Batch.
Yeah.
Okay, thank you. Third question is a little bit related to Python packages. So it's from Hayden Feach. He asks if Andrew NG recommends, oh, well, he says Andrew NG recommends always using the pseudo inverse of matrix when calculating the normal function. Is that something you recommend as well? So just for like everyone else who may not have an idea of Andrew and Jay's recommendation. So pseudo inverse is a generalization of matrix inverse when the matrix is not invertible. So when the matrix determinant is 0, it's not invertible. So he asks if you recommend the pseudo inverse of a matrix as well, If so, which Python library do you use to calculate the pseudo inverse?
Good question. So you're totally correct. And Reggie does recommend pseudo inverse. In Python, most of you can use it with NumPy. I know you can like calculate pseudo inverse with NumPy. If I can remember it correctly, I might not be 100% sure. But if you want to use, or if you want to implement the closed form solution by yourself, I would recommend using a regularized version. But yeah, you can like definitely calculate. I'm not sure, but I need to check pseudo inverse NumPy. Yeah, so yeah, NumPy linear algebra has P inverse.
Okay, that's good. And the last question is actually about regularization. I feel like these questions are all related to each other. So it's from A Sal. He asks, can you comment on how GDA? Sorry, I don't know GDA. Is it gradient descending?
Gradient descent algorithm.
Oh, algorithm. Okay.
Yeah.
How the gradient descent algorithm works for lasso regression?
So I guess for this question, I'll post a link in the Slack channel that I talked about like a couple of moments ago. But how, when you implement the lasso regression or any kind of regularization, lasso means L1, and what I discussed here was L2. L2 is known as ridge, lasso is L1. But when you implement any kind of regularization, you change the cost function. You don't change the algorithm. So when you change the cost function, I believe you should be able to implement the gradient descent algorithm because it takes the derivative of the cost function and updates the parameters. So it doesn't affect the GDA algorithm at all. So the GDA algorithm will be the same, but the only change will be in this cost function. In case of L2, it will be L1. So that's what I think of it. Does that answer your question? I don't know.
I think it's a good answer. Okay, now we answered all the questions before the break. We can take a 10 minutes break and then start the next section with a new presenter at 14:26. Yeah,
Okay, I
just
think
for, yeah.
yeah, sorry, I think there are like more notebooks to go through. So I guess I'll increase the pace.
Okay. Oh,
Yeah.
okay.
Yeah,
Oh,
yeah.
sure.
I need to go through like notebook 2 and Sora will go through notebook 3. And 4 and 5 are like really quick because they're like coding, so it shouldn't take much time.
Yeah. Okay.
Cool.
Okay. See you guys at 14:26.
Yep. Just went on YouTube for like 5 minutes and I saw that there has been a launch from Kazakhstan to the ISS. So if you're interested, check that out. Okay.
Sorry, say again.
There has been a launch from Kazakhstan to the International Space Station. So if you're interested, check that out. Yep. I'm interested in space stuff, so thought you guys should know. Okay, so getting back. So in the second notebook, what we're going to talk about is linear classification. In the first, we talked about regression. Now we're using the same concept to classify between classes of data. Cool. So here's how a linear classifier looks like. So you have like data points in this case, it's a three-dimensional space. And this green line or like a plane that you see here is called a hyperplane. It's called a hyperplane because this plane can be extended to n dimensions, so n-dimensional hyperspace. A cool thing, even though we can't visualize, but yeah. And the job or the task is to linearly separate between k classes of data. Okay, in this case, k equals 2. and this hyperplane separates the two classes in 3D space, and you want to extend it to n dimensions. So the easiest and the most simplest classification model is making the prediction, and if it's like negative, assign it to one class. If it's positive, assign it to other class. And sign is basically representing that. So positive and negative examples. If it's the product is negative, assign it to one or the other. Okay. And as I said, sign is the signum function that returns the sign of the argument. In this case, it's W transpose times X. So one of the most prevalent linear models for classification is called logistic regression. And here's an example where there's a bank and they want to decide whether they should give a loan to a person or not, depending on what is the probability of them defaulting on the loan. So defaulting means you're not able to pay off the loan, and yeah, so you don't get the loan basically. So they have like set a threshold that if the probability of the person defaulting on the loan is greater than 0.15, they deny the loan to that person. And if it's like less than equal to 0.15, they give the loan to that person. So approve the loan. And this is the equation, and it follows from the last notebook, the probability of yi equals 1, so approval of the loan, given the input x or the person and the transformation matrix W. Cool. So what we have here is called the sigmoid function. It might seem a bit disconnected, but I'll make sure everything gets together in one beautiful form. So what we have here is the sigmoid function. So um, the sigmoid function takes a form of this. So 1 divided by 1 plus exponent of minus z, and z here is W transpose X. So if you like solve this for any z, you will get a value on any of this, on any point in this curve, on this curve. So that's how the sigmoid function works. And usually what we do is if the value of z is like greater than 0.5, we assign it to a classes of 1. If it's like just less than 0.5, we assign it a class of 0. So that's how like the sigmoid function works. But the sigmoid output can be any point on this line. So any point is just wanted to make that clear. Okay. So how do we like so I just explained how the sigmoid function works. And let me navigate here 1 second. Yeah, so our job is to like classify between two classes, and we make the prediction as we did as always, like W transpose X. This is one thing, like the log odds ratio. The odds ratio is like this one, so probability of the event happening and not happening. And then we like just simplify this expression and we get like this one. So if you plot this is like just a derivation of how this function actually, why the function looks like this. Okay, so this is just a derivation. It's not important, but just wanted to go over it. And what we usually do is we try to predict what is the probability of yi, or the output equals 1, given the input x and w, which is nothing but the sigmoid function in this case. Okay. And so maximum likelihood estimation and logistic regression. So we use the same idea of MLE that we saw in the last notebook and apply it to the logistic regression model. So the only difference here is the loss function, and loss function is like a sigmoid function. It's also called the logistic loss. So for probability of X being classified into a positive example, is probability of yi equals 1, or the positive class, given the input x and w, which is nothing but this. And it can also be represented, and the other class can be represented as 1 minus the probability of the first class, right? So this is what it is. So probability of xi being assigned to the negative class is y equals -1, and that is nothing but 1 minus this one. You can also represent it as this one, okay? And so if you combine that, this is how it looks. And if you like look at it closely, y can take a value of 1 and -1, so that's why it's multiplied by y. So it can be +1 or -1 here. So it like nicely brings it together in one equation. And this is, I'll go over this a bit later, but this is nothing but, this picture is an extension of this. So I'll just like go over this one. So this is nothing but the representation of how you can think about how good our model is. So this is like, let's say, one line, and this x1, x2 should be in the upper half of the line, but it's actually not. And this is this also should be like up in the, sorry, this x1, x2, and x3 should be positive. x1, x2 is not. X4 should be negative, but x4 is classified as positive. And so what we want to do is we want to calculate the error and fix this. So how do we fix this? Again, we go back to MLE and we try to adjust the parameters to set the derivative to 0, the derivative of the loss function to 0, and calculate the parameters. It's the same concept. So if you remember from this one, so this is our logistic function. The probability of y equals yi given xi and w. Same thing here. If you want to maximize the probability, we find the product of all the occurrences. And we take the log. So if you take the log of a product, it changes to summation. And if you remember that this probability is nothing but the sigmoid function, which is 1 over 1 plus exponent of this one. And if you simplify this, it changes to this. And this is your loss function, okay? And we want to like minimize this. This is also called the log likelihood or the logistic loss. It's the same thing, just different names. And this is like specific to the logistic regression. So we see that how for different linear models, depending on the task, our loss function is different. Okay, so so again, like if you want to get the parameters W, you take the derivative, set to 0. And what I got from this image, it wasn't clear, and I think this is not like a good representation of what the author was trying to like portray here. But what this generally means is that, let's say you have a binary class, and if you like have a product instead of the log loss or like the 1-0 loss. So if you get like a prediction correct, you don't update the weights. If you get a prediction wrong, you update the weights. But when you update, you like just flip the value of the weights. So it becomes a 1-0 loss. And if you like have a 1-0 loss, you will have like this step function. So initially you have like an incorrect prediction, and then you have like a correct prediction. So you subtract 1 from the weights, and then you have like 0. And if it's like less than 0, you set it to 0 anyway. So this is like a very bad loss function. So you don't want that. And log loss gives you like a smooth curve from a high error to like the close enough or close to the true error. So this is what you want to use, and the blue line is what you don't want to use. And this is like just the same thing. It's like just an expression of what this log function is, nothing complicated. Okay. And now, how do we implement L2 regularization? We saw like L2 was implemented in case of linear regression, But how do we implement that in case of logistic regression? So you have the log loss function, which is nothing but the sigmoid function. And we want to add one term, which is the weight matrix, and we multiply that with lambda. And this actually, again, transforms the loss function. And somebody asked like how GDA will vary. GDA won't vary. The only thing that will vary is the loss function. So we change the loss function. And when we add this additional term, the loss function changes its form, and it becomes this. Okay, and C is the regularization parameter. Okay, and one more thing to closely observe is, if you're like looking at the notebook, is C here equals to 1 over lambda. This is done because in scikit-learn, the C value for logistic regression is like the inverse regularization parameter. So lambda is the regularization parameter and C is the inverse of that. And I don't know why that's the case, but that is how it's like implemented in scikit-learn. Okay, so just to make sure. So in case of scikit-learn, the higher regularization parameter, the larger the lambda value is, the smaller the regularization, and smaller the lambda value is, higher the regularization. Opposite to what I explained in the last notebook. So make sure you keep that in mind. So yeah, if you want to like explore more on this, there is an assignment. You can go over and do the assignment. But I guess I guess it's time for questions now. And after the questions, I'll hand it over to Saurav and he will go to the third, the third notebook. So are there any questions?
I think we have only one question, and it's before the break. It was posted right before the break. It's a hypothetical question. So Conavolt asked, if you overfit a sample data set that can perfectly represent the actual population distribution, is this still a problem?
It's not a problem. So if you overfit on a sample data set and it perfectly represents the actual population that, or you get any data later that you want to implement or like test your model on, that you fit on the sample data set, it's not a problem. I mean, the whole point of implementing or training a model is to make sure it generalizes well. And if you overfit on a sample data, and by the term overfit that you're using, you're implying that your training and test samples come from different distributions. So if you like fitting on a sample data that perfectly represents the actual population, and you are 100% sure that the model will be giving you almost 100% accuracy on the test, then there's no point to like go through this techniques called cross-validation and all that stuff. But by saying the term overfit, one means that your training and test data are so different that your model is not able to generalize on test data. But by your question, if you have like a sample data set that perfectly represents the dynamics of the world, then there's no like point of improving the model. You just train on the data set and use it everywhere. So it's like, yeah, if that answers your question. But that's a good
Okay.
question though.
Yeah, I think that, and that's the only question.
Okay, so I guess I'll hand it over to Saurav. Saurav, are you there?
Yeah, I'm there.
Okay. So I'll just stop sharing my screen and you can go ahead.
Can you see my screen?
Yep.
Okay, and this is Shorop, and I'm the participant, MLA Bootcamp, and I will talk about the regularization.
Um, Sora, do you mind give us a brief introduction of yourself so we can connect with you?
Yeah, okay. So I'm doing my master's in management analytics. So I'm coming from business background to machine learning. So I'm pretty much new in machine learning sector. So um, okay, my slide is changing. Can you confirm that one?
Yep.
Okay, sounds good. So first I will talk about what is regularization and why. So it's a technique that applied in cost function in order to avoid overfitting. Actually, overfitting create like when our development and test set come from same distribution, it might create overfit, and also overfit can create and when function is too closely fit in a limited set of data point. So and regularization keeps more important feature and ignore unimportant ones, and also it reduce the variance of the model. Like from here is like it we like a Andrew and G book, like I found like that we can split the data set into like training error and development error. So when training error and development error is the difference like 10%, like it's create the variance, and the data will gonna be create the overfitting model will create the overfitting, and regularization can apply to reduce the overfitting. So there is a three types of regularization: L1, L2, and dropout. So L1 is a lasso regression, and L2 rich regression, and dropout is applied for deep learning. I think Rohan mentioned that before that, and also I found from the Andrew ng book. So this is the cost function J beta, and here is M is our number of data point, and N is parameter like feature. So the first part is training data, that it is our cost function, and we applied for a regularization parameter so that it will reduce the overfitting. So if lambda is too large, that it will create underfitting, and if lambda is too small, and it will create the overfitting. And you will find the more details in Andrew and G books. So and this is actual picture like when you see that there's lots of variance, let's, and this is overfitting, and this is just right, that one. So that's actually like basic thing, and I'll go to the notebook actually. Do you guys see that my notebook?
Yep.
Yeah.
Okay. So here first we just load the packages. So scikit-learn we also use the panda and numpy, and the second we read the data set. So this is the microchip data set, and there is 180 microchip data set, and this data set represent like whether it will went to the production or not. So and we also get the information about the data set. And the third one, we inspect the first five lines and last 5 lines. So that is like head 5, so that shows the test 1 and test 2, and before that we label also header 1 none, test 1, test 2 released. So that is reflection here, and this is the last 5 line. And here we save the data in X, Y, and Y. So we'll work on different like a target value like levels. So that's why we just save in different level the original data set, so X and Y. And here we create the plotter. Actually, we create the plotter, plot the data. So orange is we organize as a defective, and blue we mention as a normal data set. So there is a reflection. You can see the blue is normal and orange is like a defective one, and it's labeled by release and faculty. So the number 7, we just classify that, separate the curve out to the classifying. So basically we create a boundary for that one. And if you go here, we applied for like a polynomial feature, and we presented a degree 7. And if you see, there is a polynomial shape is 11836. So this is the one, like we're gonna be apply the logistic regression. So my regression parameter is C is regression parameter. So first we apply for 0.01. So when it's 0.01, that is that one. And again we will go to the little bit more, like 1, and then again we will go to the 10,000. So that's happen here. So first we go to the 1. So parameter 1, this is looks like. And when we parameter 10,000, like if you see 1 exponential e4, so that's been 10,000. So that looks like. So, and that's the part actually, and rest of the part will Rohan will continue that one.
Okay, I guess you can see. Yeah, sure. Thanks. Cool. Cool. So I think what Saurav explained was up till regularization.
Yeah.
Just before that. Yep.
Yeah.
Okay. So, so I would like encourage you guys to like actually go through each of the cells and try to fiddle with the parameters and see for yourself what happens. Um, but in essence, what was happening is um, you have the data set, you train a model, and the model is from scikit-learn. You plot the performance of the model, you fiddle with the parameters, and just see the change in the plots. Okay, so that's what the idea of the first half of the notebook was. Um, so what I'll just give you an overview here is how you can like expedite the process of tuning the regularization parameters. So by tuning, I mean you change the value of the C, which is 1 by lambda, 1 over lambda, and you inspect the change in performance of the model. Okay. So what in this part, I won't like run this because I haven't run like all the other cells before. But I'll go through all of the cells in the later notebooks. So what's happening here is you have a stratified K4 cross-validation. If you don't know what cross-validation is, I'll talk about it in just a second. But you basically make different sets of the data set, different subsets of data, different training and testing subsets, and you assess the performance on each subset of that test data. So you train on some part, test on some part. You train on another part, test on some other part. So that's what cross-validation is. And the C values that is being used are being used is like defined over a logarithmic space, 500 elements from -2 to -3. Sorry, -2 to +3. And you're basically using the logistic regression class, and you're doing cross-validation on that. So before I move on to something else, let's see. Okay. Question? Chat? Yeah, so I'll explain that. So on what basis do I? So this is like another notebook. Don't tell anybody. This is like from a class that I'm TAing. So I created the notebook for that. So cross-validation. So this is your whole data set, okay? The total number of samples are in the available data. So there are primarily two types of cross-validation. One is called the simple vanilla cross-validation or just cross-validation, and the other one is called Monte Carlo cross-validation. So the simple cross-validation, you let's say have 100 samples from, let's say, sample 1 to 30 is your first test set, and from samples 31 to 100 is your training set. This is for iteration 1. For iteration 2, you have samples from 1 to, let's say, what is this, 30 as training, and from uh, 60 to 100, let's say. I know it's like divided by 3, so it should be 32 point something, but yeah, anyways, you get the idea. So this part and this part is the training set, and this is the test set. And in the third iteration, you have this is the training set, and this is the test set. Okay, so how cross-validation works is you train on this, train on this, train on this, train on this, and on each iteration you test on a different subset of data. One thing to note here is all the test sets are mutually exclusive or disjoint than the previous or to the previous iteration. So you don't see like any overlap between the iterations. Okay? And this is called k-fold cross-validation, or like generally vanilla cross-validation, simple cross-validation, where k equals 3 in this case. Okay. And the next type of cross-validation is Monte Carlo cross-validation. So in case of Monte Carlo, what happens? You initially set a fixed test data size. So let's say you want to use 20% of the data for testing, rest 80% for training. One major difference, and I guess it's the biggest difference between K-fold and Monte Carlo, is there is overlap between the samples among different iterations. So in the first iterations, you have like this sample, or the blue bars are the test set, or they're like combined to create the test set. In the second one, you have like, you see like this bar is overlapped. So it's not guaranteed that different iterations will give you different subsets of test data or train data for that matter. And it's the same for the third experiment. Now it's like easily observed from this that okay, I guess I'll ask this question to the audience. What do you think the advantages of K-fold and Monte Carlo is in terms of like assessing the performance? Can either type it in the chat or yeah.
I guess that Monte Carlo goes for a more deep variation in the data set in the data that we are using to train the model. So I think that it could be a advantage.
Okay, yeah, that's a good example. Anything else?
There is a break in the data set, structural break.
So what do you mean by structural break?
So the function change, let's say, I don't know, inflation, for example, for economists, inflation in the 70s and inflation in 2000s look like different completely. Right? So there is a structural break.
Yeah, if that's the case, then I would say like your data is different. So there are like two different data sets and not one single data set. I mean, it could be one single data set, but the distribution or the parameters change. So in that case, I would recommend like if you are training one single model, then it's like very difficult to generalize between two time scales because as you said, like inflation in like early 1900s will be like totally different from 2000s. So how do you get like one parameter that will like generalize across two time scales? Like one very interesting question, I guess. But what I was getting at is the number of iterations or number of times that you can run the model is basically infinite for Monte Carlo, if you expect. Because in case of K-fold cross-validation, you can have only finite number of distinct sets. But in case of Monte Carlo, you can have literally unlimited number of training and test subsets. Okay. Yeah. And yeah, so that's how cross-validation actually works. Yep. Fine. So I think that's clear. And I think you guys have like a good understanding of what this cell is doing. And this is nothing but like the best parameter that gives like the minimum squared value, minimum loss. So best parameter of C that gives the minimum loss. And this is nothing but like just printing the mean cross-validation accuracy. So as I like showed you in this picture, like how different subsets of the data are being done in order to like assess the performance on different data sets. So this is like the mean cross-validation accuracy depending on the C value, the inverse regularization strength. So let's say for 0, it has like somewhere around like above 80% or something. And as you increase the value of C, what happens is like, since it's like the inverse regularization strength, it doesn't basically make a difference. So in this data set, it doesn't, but it might make for others. But in this case, it doesn't. So the accuracy rarely changes, or the mean cross-validation accuracy rarely changes. And for any machine learning project, I would recommend like implement some kind of cross-validation. There's also like another variant called the nested cross-validation. So you also might want to look into that. Okay. Question. What is the main data structure for a requirement to use Monte Carlo or K-fold cross-validation? What is the main data structure? What do you mean by data structure? Like something to store the data in? Like what's your, why do you need a data structure to get like the do cross-validation? I don't know if you want to unmute yourself and like talk, but can you like unmute yourself and talk? Okay, not. Okay. Fine,
Okay.
I guess. Yeah, sorry,
Yeah.
go ahead.
Yeah, my question is regarding when do you use Monte Carlo or when do you use Cafol? When do you choose between them? What is the, despite the fact that you can do several iterations in Monte Carlo, uh, when it is preferable to use Monte Carlo and when it's preferable to use a simple Cafol cross-validation?
Yeah, good question. So the first thing that comes to my mind is the computation power. Okay, so if you have like, if you're using some kind of cluster like Compute Canada or something, then I would always recommend do like a Monte Carlo version of cross-validation, because every iteration you will have almost like most of the time you will have a different subset of the data set as test data. So your model or like the overall performance will be like more generalized across like different iterations. So you'll have like a better understanding of what any um, permutation of a subset or like any combination of samples from the data set will give you like some kind of performance. But if you're like limited on computation and if you want to run your algorithm a fixed number of times, or you want to have like a very high level idea, not so like deep understanding of what's how your model is performing on different subsets of data, then I would like recommend going for K-fold cross-validation. Does that answer your question?
Okay.
Yeah. Okay.
Yeah. Thank you very much.
And how would you train and test split a hypothetical data set with n equals 650, but only 250 values that have labels to train on? I mean, usually it's 70-30 if you have like all the labels, but is there, if there is like n equals 6, if there are 650 samples and there are only 250 labels, then like you have 400 values or like samples that have no labels. What you're going to do with that? How are you going to assess the performance? So in that case, either you can do like get the labels for like the 400 samples somehow, or you can discard the data set. But in order to like assess the performance, you need some basis to compare to, right? So let's say you train on 100 samples and test on 50 samples. Those 50 samples you make predictions on. You want to compare the predictions whether they are correct or not. How would you like compare the predictions if they are like no um like no basis to compare to? You can certainly do a clustering or like unsupervised classification or like semi-supervised, but yeah, I think that's one of the suggestions I would make. Yeah, somebody posted. Yeah, fine. Yeah. Okay, so now that's done. I think it's a good time to move on to the next Jupyter notebook, which is notebook 4. And I guess I'll actually go and run the execute the cells. It's better for you. Okay, so one thing, if you want to actually run the codes or run the cells in the notebook, I found it like a bit difficult on Google Colab. I was able to like clone the repo, but I wasn't able to like open the notebooks, and so I'm just using Jupyter Notebook on my local machine. Fine. So this problem is classifying Internet Movie Database IMDb movie reviews as positive or negative. So some kind of sentiment classification problem. It uses text as features, so some kind of NLP problem, and I think it's good. So yeah. Okay. So here's what the data set consists. So like 125,000. Sorry. Yeah, something like that. Um, so you have like how many are there? Yeah, so you have like equally divided data set, 50-50, good and bad, and you have like reviews. This is like an example review. What the tokenizer does is it separates this sentence into individual tokens. In this case, one token is one word. It builds a vocabulary over all the reviews. So this is like one review, and this all these other words might be in some other review. So it creates like a set or a list of all the, yeah, it's a set. So there's no repetitions. So set of all the words, which gives you the vocabulary. We call it as a vocabulary. And then for one review, you will have a matrix encoding, and this is called a one hot vector. So wherever you see the word, you set the value at that position as 1 and rest of it as 0. So for ants, you see like the position as 1. For get, U1, U1, and rest of them are 0. So this is called a sparse matrix encoding. Why is it called sparse? Because there are a lot of zeros. You can imagine like a vocabulary can be like 10,000 element long vector, but one review can be like, how much is it? 6 words. So like in case of like, for case of 6-word or 6-word long review, you will have only 6 ones in the 10,000 long list. That's why it's called sparse. Okay, so go ahead and run this. I'll also run this. It's connecting to my local. Yeah, it's done. And this is like just downloading the data set and all that stuff. It might take some time. But yeah, let's, till that happens, till that completes, I'll go through, execute the rest and just wait for it. Okay, so this is an example of a review. So you have like the stored in binary format, and this is like a separator. It's not important, but just to give you an overview, this is what a review looks like. So, man, this is a big review. Okay, fine. This is like one example of a bad review. So yeah, let it like run. And this is like another review. So yeah, this is one good review. Um, so, okay, I think I should also explain this how data is being separated just to give more context. Man, it takes a lot of time to. Right. So how it works is you first load the files and you have the categories as positive and negative, and you separate the data set into training and test data. So in case of this data set, if you like use the load from scikit-learn data set, it's like an inbuilt data set. So it has like already separated categories of positive and negative reviews. So that's what it's doing here. But in case of your own project, you will not have this, and you will have to like manually maybe use NumPy or pandas to uh, like cut the data set at some point, or like retrieve only those samples of positive and negative, and then create the training and testing data set. Okay, so why is it taking so much time, man? Okay, it's done. Anyways, so that's how the data set is being like separated into training and testing. Okay, because in the original like collection, it's already been separated. So you don't have to use like any kind of train test plate or something like that. Now, what we do here is we use a class called count vectorizer, and what it does is basically counts the how can I say this? Create a dictionary of all the words in the data set. Okay, so creates a dictionary, and how you do is you implement the count vectorizer class. You fit the text train, so create a dictionary from the training set. We don't want to do it from the test set because that will be cheating, because you already have information from the test set, so we don't want that. Is it done? No. Okay. And we just like print the number of words in the training set or the vocabulary. There can be repetitions, but those repetitions are only considered as one. So this is like the number of unique words. And this is like without, we haven't like processed any of the data. So we haven't removed stop words, punctuations, or any kind of all that stuff. And we just get the first 50 feature names, which is like the words from the dictionary, and print them. And this is from like 50,000 to 50,050. So that's what's happening here. This is nothing like important, just like inspecting the data set. And you should all do in case you're like leading a machine learning project. Okay, so now what we do is we, as you saw earlier, that we transform the reviews into a sparse matrix encoding. So that's what is happening here. So we use the cv.transform. Cv is the count vectorizer class. We apply the transform function on the training data set, and we create xtrain. Okay. So now xtrain is like a matrix of many one-hot vectors, as I showed you earlier. So if in the position of the dictionary, if for a review, if that word exists, so the position is set to 1, and rest of the words are set to 0. And yeah, so this is an example where I wish I could run this. I guess it's still running. Okay. There's an example where like 19,726 position, this is the review. And this is like the one hot vector, but like only at the non-zero position. So this is like the indexes of that where the value is non-zero. Okay. And yeah, so that's how you can like inspect the data for. And this actually is a size of equal to the vocabulary size, which is like 74,849. But we are only like printing the non-zero. So you can like just call the non-zero function on this and get only the positions where the value is 1. And now we use the same transformation that we applied on the training set and use it to like transform the test set. Okay, so now that's how we get the X test. Now note that we are not using the transformation or the count vectorizer that was fitted on the test set. We are only using from the training set, because if we do it from the test set, then we'll have information from the test set and that will be cheating, right? So we don't want that. Question? How do you choose a random state hyperparameter? You don't. Random state is random, and if you want to replicate results across different calls, then you set the random state to some fixed value. Okay. This is like usually common when you're, let's say, writing a research paper and you're uploading it to GitHub so that others can replicate your results. And so how did I choose 7? It's totally random. You can like set it to 151515. It's totally random just for replication purposes. So if you run this code and if you have the same value as 7, you will get the same results. So that's like the point of replicating. Yeah. Okay. By default, random state is set to none. If you like inspect this, nice, it's done. Okay. So if you inspect, I'll just go ahead and run this. I'll explain that. Hold on. Cool. Yeah. So now if by default, if I inspect this, can I inspect this? Nope, never mind. Okay. By default, the random state variable in any kind of machine learning model that you use outside from scikit-learn, not outside, the random state value is set to none, even in the train, test, split class, which is like used to divide the data set into training and testing data sets. So you use like none. If it's set to none at each iteration, at every time you run the algorithm, you will get a different like starting or random value. So starting point in case of models, and like training in case of like training and testing splits, you'll have different like sets of data. Okay, and then you like just fit the logistic regression model on the X train and Y train, and Y train is basically um, a collection of zeros and ones, and if 0 it's like a negative real, 1 is a positive real. So it's like a binary classification task. You have the input as the sparse matrix encoding, which is the review's one hot vector, and the output is a 1 or a 0. Okay. And so I run this. Did I run this? I did not. Let's run this. It will take some time because it's like a sparse matrix encoding. It's like very huge. It takes 5 minutes. Sorry, 5 seconds. And I just print the accuracy, and the accuracy is like 86.3 on the test set, and on the training set it's 98.2, which I think is like a pretty good generalization on the test data. Okay, let me see if there are anything. Yes, it's exactly the same. So the way you select a random point in case of the gradient descent algorithm, the idea is somewhat similar because the starting point is different. So you get like different results every time. So let's see, can I rerun this? And then if I reprint this, are the results different? Were the results different? I don't know. It certainly did take like less time to like run, 4.4. And if I run this, it's 86.3. So yeah, I think the results are like, oh, right, because the training and the testing data set is different. Fine. Sorry, the same. If you like change the training and testing data set, then I'm certain you will get like different results. But yeah, so starting from a random state in this case, because it uses this optimization algorithm, the time it requires to train the model will be different because the starting point is different. Okay. And this is like just a function that does this visualization, beautiful visualization. I'm not going to explain this because anybody can like go and look up the matplotlib documentation and do this. Okay, and so I'm just going to run this. And so what it does is basically, hold on, let me check. Yeah, so like these are the, yeah, so these are the features or the words that are present in the reviews that are associated with positive and negative reviews. So this is like pretty interesting. So if you look at it, look at the, can I like zoom in? Yeah. So boring, worse, mediocre, humble, these are like associated with like negative reviews. And touching, fight today, perfect, even though today is like really ambiguous. I don't know why that is. Outstanding, Stallone, delightful, perfect, gem, subtle, it's associated with positive reviews. Okay, so that's pretty interesting. So you can see like how from the model training process, we extracted the features, and the model is telling us that these are the words that are associated with positive and these are the words that are associated with negative. So that's pretty interesting. Where is the logic coming from? Okay, so logic is the logistic regression model. All right, so moving on. Now, a make pipeline. So what is make pipeline? I know this is like slightly disconnected from the theory part, but this is like more of how you could use these functions for your own machine learning project and like just structure it in a way that is like acceptable as per software standards. So make pipeline is nothing but a series of operations that you define on the data set from the start to the end. So it's like a production pipeline if you want to relate it with that. So pipeline is a series of operations. First you do the count vectorizer as we like did before. We did the logistic regression, and then we like just have the score here. So you can always like not use make pipeline and just write these in like different cells. That is fine too. But just to like save some space and make like things pretty, we're using the make pipeline function. Okay, so go ahead and run this, and it will take some time, and then it will like print it. It has no benefits for like performance. No. Just a way to make things prettier. So imagine like a black box. So make pipeline is a black box, and inside that black box, there are like many operations. Let's say you're like explaining something to a client. You don't want to like explain everything that's inside the black box. You just say, okay, this is the model, this is our system. You get the data, and this is your output. That's it. So you don't want to explain everything. Use a make pipeline, put everything in it, forget about it, and just use that pipeline as a black box. It's kind of like an abstraction from software engineering. So you abstract many of the things and use a black box to encapsulate a lot of functions. So yeah, anyways. Now, this is one of the important things. So hyperparameter tuning. So grid search. So hyperparameter tuning is like one of the crucial, I would say, components of any kind of model fitting process. So in case of logistic regression, you have a parameter called lambda, because by default, if you go to the documentation for logistic regression, you will see that, let me just show you logistic regression. Yeah, so the penalty by default is L2, which is nothing but the ridge regression as we saw earlier. And it has like a C value of 1, which is like the default. And what we are, whoops. Yeah, and what we're doing here is setting the C value to like different values and inspecting the output. So grid search is actually helpful for us in that case, because it automatically takes all the C values that you give it and then trains the model with each of the C values and then gets the output, and then you can assess the performance on your test data. So that's how it works. It's like it's nothing but repeatedly training on the training data with different values of the input parameters. In this case, it's C, but you can like basically change any of the parameters that are there for the model. Okay, and so that's what's happening here. Um, so grid search takes in um, the pipeline. Is that, yeah, that's right. And takes the pipeline, it takes the parameters. So in this case, you're changing the C value or the penalty parameter for logistic regression, which is nothing but this one. And then you're like defining some values that it will test on the training data. You're doing a threefold cross validation. It's called, this is not Monte Carlo, but like the simple k-fold cross validation. You're like doing this three-way, and n jobs equals -1 is just using as many CPUs as it's available. So this is like more of multi-threading, not important to this machine learning thing. Okay. And finally, you take this grid search um, class that you instantiated or instantiated and give it the training and the testing data. So it'll take a lot of time because it has to like train over all these parameter C values and then also do like a threefold cross validation. So it will take a lot of time. And then you like print the best parameters and you also print the best score. So grid search has this like attributes. Yeah, so it like trained and it like gave me the best parameters as 0.1 in this log space that I defined here from -5 to 0. Huh? Yeah, what happened here? Yeah, so 0.1 and then um, you have like a best score of 88.5 for that best parameter. Okay. So this is the parameter grid. It's an array of uh, 1 to the power minus 0. Yeah, minus 5, -4, -3, -2, -1, and 1. So that's what happened here. And for 0.1, which is I guess this one, you have like the best score. So it turns out that for okay this training and test data set like division 0.1 works best. Now ideally what you want to do is like for multiple divisions of training and subset, which is called the nested cross validation. So that's one more thing. And this is nothing but the training and the testing scores. So obviously, like it's pretty obvious that okay, for the training, you'll get a higher score than the testing score, but that's how it is because you're training on the one data set and testing on another, even though they're from the same distribution. But yeah, that's how it is. Okay. And for the validation set, you have some accuracy. Which is nothing but like getting the score on the test set. Okay, so it's 87.812. I'll answer the questions in a bit, but let me just go through all of these. Go through this real quickly. I haven't like explained what random forest is and how random forest works, but random forest in general is like a collection of many decision tree classifiers. So decision tree, you can, if you know how a normal tree or a binary tree works, it just takes in many features and it uses some algorithm to choose what the best features are and then classifies the samples between one class or the other class. So that's how our decision tree works, and random forest is like a many collection of many decision trees. That's how it is. Okay, and so if you I won't like go into this because it's like uh, a bit disconnected from this all the previous part that we discussed, but I'm gonna run it anyway, and it's gonna take some time. Till it runs, I'm going to like show you one problem, which is called the XOR problem. This is like one of the simplest problems that or where a binary classifier doesn't work. So if you have taken like any kind of computer science course or electronics course or like um, yeah, Boolean algebra course, you know that what an XOR gate is, right? So if you have the input as 0 and 0, you'll get a 0. If you have like a 1 and 0, you'll get a 1. If you have like a 0 and 1, you'll get a 1, and 1 and 1 is 0. So different inputs, 1, and the same inputs, 0. So that's what the XOR gate is, or exclusive OR, if you want to have the full form. So yeah, so first what we do is we create a data set of XOR values, okay, 200 samples and 2 columns, so column 1, column 2, and we scatter them, okay. And so if I comment out the random state, uh, okay, I need to like do something else to like comment out the randoms. So if I if I change the random state, what happens? I think I got a different plot. Yep, I am getting a different plot if I change the random state. So set it back to 0. So I get this. And this is nothing but plotting the x and the y values, eh? So yeah, so we have like 200 samples of x and y values. And this is just another helper function that helps to like plot the boundary, this like division that you see here and this division. Okay. And so let's use our logistic regression class on this XR data set as a binary classification problem and see that it won't work. So you see that this white narrow band in between is not able to like differentiate between the light blue and the, what is this, orange or dark orange classes. So we want something complicated. So a simple logistic regression of binary classification does not work. So we need to do something to the data. And that's how, or that's where the polynomial features come in. So polynomial features at a very high level is like transforming the data to a higher dimensional space. So now instead of having 2 features, it has more than 2 features. Okay, and this case we have like a 2-degree. We said the degree equals 2, so like it for every feature in the data set, it like has another feature that it's basically just a multiplication of the same and the other, or all the variables basically. So let's say you have like input 1 and input 2, so you will have like a new feature as input 1 times input 2, input 1 squared, input 2 squared. Okay, and now if we apply the logistic regression on the data set plus quadratic features, that is, as we had the polynomial features applied on the data set, now we see that logistic regression works good because it has like more data to classify the classify the points into different classes in the visualization shown here. So yeah, polynomial features work well if you want to have like higher order features or more complex features. If you have like many features, then obviously it will take a lot of time and you also might run out of memory. So use it carefully. I have like 1,000 samples, let's say, and for my project, I had like 1,000 or 2,000 samples, sorry, 2,000 features. And I did like a polynomial features with degree 2 and my memory ran out. So because you can imagine like it has to multiply each of the 2 features and get a new feature. So only use it if you have like very less features. So just saying. Fine. So in this notebook, we looked at how we can use logistic regression in practice. We also looked at grid search, hyperparameter tuning, and also polynomial features. So before moving on, I think we're okay on time. We're moving on to the next notebook. I'll look at the chat. So setting a random state is not different from setting a random seed. So it's the same thing. The only difference is that um, setting a random seed, if you want to like generate a lot of samples, let's say as I did here, where is it? Yeah. Um, you can either set the random seed for like, I think, yeah, I guess it's the same. There's no difference. So, but I would say like random state is more prevalent in function calls or like class instantiations. For example, um, in case of the logistic regression class, there is like a variable called random state. Just sets the starting point of the optimization algorithm. But like in case of a random seed, you will probably use it with NumPy, and if you want to like generate a set of numbers, and if you want to replicate results across different runs, you will set like one random seed. So basically the same thing. Okay, other questions? What's the difference between make pipeline and compared to just def function? I guess what you're asking is, what is the difference between def function and make pipeline? Or how do they two differ in terms of the application? Okay, so if you want to unmute yourself and explain that more, I don't want to. I just give my opinion from what I understand. So what make pipeline does is it assembles a series of operations into like one single operation. So first, in case of this make pipeline, where did it go? We have like the count vectorizer. So you'll take the data, apply this count vectorizer on it. Then the output from the count vectorizer will be fed into the logistic regression, which is nothing but the sparse encoding. And then you do whatever you want to do. Okay? But in case of a def function, which is like the way to define functions in Python, you can like do the same thing. So you can like create a function called def make underscore pipeline and like just write instructions for like, let's say you in the first line, you inside the function, you type in count vectorizer, do the fitting and all that stuff. And then before the function ends, you can like do the logistic regression, do the fit and all that stuff. It's the same thing, but this is like more short and it's like more pretty to the eyes. So that's the only difference. But in a way, you can do the same thing with the def function. There's no difference. Lead, can you select what features to apply polynomial features to, or does it apply to all of them every time? Obviously, you can select what features you want to apply the polynomial features to. And how would you do that is by, where is that? In case of pipeline, it's slightly more complicated, but what you can do is here in the plot boundary, just like select, let's say some, let's say since here there are like only two variables, so I'll just select some of the features and then just feed it into the polynomial features class. So let's say you have 100 features, right? And you want to only apply polynomial features on the first 50. So you just like subset the data. So let's say you have X, you select all the rows, which is like the first parameter here, and you select only the first 50 columns like this, and then you apply for polynomial features. Now, how do you select that features? That's a different question. I mean, you have to do some statistics to find out which features are actually important. Maybe you could do like PCE or something like that. Yeah, principal component analysis. I think we have later what PCE looks like, but yeah, you can do something like that. Okay, so no other questions. I'll move on to the final notebook for today. It's been a long day. Okay, so more on like validation and learning curves. And in this part, we'll try to get like a closer look on how our model is performing given different parameter values. One more question. Okay, no. Yeah, I guess what they said, it's correct. Yeah, that works fine as well. Okay. Okay, so validation and learning curves. So um, this is like one of the topics where you can actually see whether your model is overfitting or underfitting, and we'll look into it later in this notebook. But to start off, let's like import all the helper functions, and using these functions, we'll try to assess the quality of the model. Okay, so the data set is different here. It's not the IMDb movie reviews data set. It's like a telecom churn data set. So trying to decipher whether or how many people are leaving the company and how many people are staying. So that's called the churn modeling problem. And basically, so we read the data set. Let's run this. And the data has a column called international plan. So let me just uh, data dot head print. Yeah, so I can see like the columns here. So account length, area code, there are like many different columns here. Churn, so does the person leave? No, 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 no. I'm pretty sure there are some true values here. So this is the person or the sample. This is the features of that sample or characteristics. And does the person leave? No. Okay, so that's how the data set looks like. And also like there's some like pre-processing that has been done here. So international plan, it was previously yes and no. Now it has been remapped to 1 and 0. So 0 was no, 1 was yes. So yeah, same with the voicemail plan. Okay. And so SGD classifier. Now we come to the stochastic gradient descent classifier. So it's nothing but similar to logistic regression, but not logistic regression. It classifies it's also a binary classification problem, but instead of using the optimization algorithm in logistic regression, which is by default this one LBFGS, what it does is it uses gradient descent to do the same. So how many iterations of gradient descent? 5 iterations. Random state is set to 17 for replication purposes. You can set it to none, or you can like omit it. Use as many CPUs as available. And we are using the log loss, sorry. So log loss means binary classification. So can we, let's like search for SGD classifier. Something comes up. No. Yep. So we have the SGD classifier here. And by default, the loss is hinge loss, which is nothing but SVM, I guess. Yes. Defaults to hinge, which gives a linear SVM. And if we have like log loss, it says here it gives logistic regression and probabilistic classifier. So pretty consistent with the documentation, and always go to the documentation for any help. Okay, so we have logistic regression in the form of a stochastic gradient descent classifier. And again, we create a pipeline just to make things easier and reduce the amount of code that we write. So initially we'll scale the data, and the standard scaler class, what it does is it takes each value in the data set and subtracts the mean from that value. And so you have like a unit variance. It follows like all the values in the data set have like the same scale. And this is important because imagine if like the total day minutes is like ranging from let's say 100 to 300, but your number of voicemail messages is like very low. If you like try to approximate the weights using this classifier, this feature will get more importance than this feature because the value is high. We don't want that. We want the features that actually have more importance to get more importance, but not only depending on how big the values are. we want the weights to decide that. We don't want the values to decide that. So that's why we scale the data. Okay. And again, we do like a polynomial features of degree 2 because we want like more complex model. And SGD logit is this the stochastic gradient descent classifier, which is like the classifier. So first scale the data, um, augment the data set by creating more features, and just uh, feed it into the logistic regression class. And then we create a validation curve. So we take the logit pipe, which is this pipeline. We feed the X and Y data. And depending on the alphas or this log space, or what is this? Yeah, so we have like the alphas, which is nothing but the SGD classifier parameters. And we use the scoring RC, AUC, or receiving operating characteristic, or area under curve, which is nothing but the accuracy at a very high level. It's not, but it's like more dives into more like true positive, false positive, and all that stuff. But just to simplify things, just think of it as accuracy. So I'm going to go ahead and run that. And it gives me a convergence warning, which is okay. I didn't break the code. And it's done. And now what I'm going to do is I'm going to plot the training and the validation scores. So validation is on the testing data set, which is nothing but the cross validation. In this case, it's K for cross validation, and K is equal to 5. And the training scores are following this trend, and the testing scores are following this trend. Okay. Now, so two things to note here. It's written here, but I'm going to explain what that means. For simple models, if the training and validation scores are close, it's like the difference between or the margin between the two scores are like close, but the errors are very large, okay? Then this suggests that the model is underfitted because the error is very large. But for highly sophisticated models, or like more complex models, um, the training and validation errors differ a lot because you're using like more features to like train your data. And if this happens, then it's a clear case of overfitting because you're getting like very high training scores on your training data, but like very bad scores on your test data. So we want our training and testing scores to be fairly close enough, but also the error should be like fairly low, not as high. Okay. So how much data is needed? So this is a question where you can leverage the idea of validation curves. So like to like assess, do you need more data, or does adding more data help you to get a better model, or does it not? Okay, so I'm just going to run this function. So it's nothing but just the same thing, the pipeline, and plotting the learning curve with some like extra things like the legend and all that stuff. But the idea here is that if the like the training and the validation scores, if they're like close to each other and they follow the same pattern, then this case adding more data will not do anything, like. But in case, let's say, and here what I'm doing is I'm setting the alpha value as 10, which is the regularization parameter, I guess, in this case. Yep. So in this case, it's like something like this. But here, what is happening is, where did my plot go? Yeah, here's the plot. But in this case, we see that initially the training, sorry, the AUC is like very low for like validation, but for training, it's like very high, and then they converge. So this means that this means that overfitting does exist, and if you like set it to like very low, then sorry, in this case overfitting does not exist, but if you add like more data, then it won't like add anything to the model. But in this case, if we like set alpha equals like very low, then we see that the score actually reduces, so the error increases, and this way like we can see like the overfitting does exist. So these are the like the validation and learning curves that you can leverage to assess how the model is performing on the data. So I'd like encourage you guys to um, read these because there are like a lot of cases written here, and go through each of these to like understand how each learning curve will give you like different kind of conclusions as to is the model overfitting, underfitting, um, or like is there, do you need more data, or does adding more data help or doesn't help, so all that stuff. Okay, so to conclude, so I'm just gonna read this out. So if the two curves are close to each other and both errors are like very large, then it's a sign of underfitting because we want our errors to be small. But if they're like very close to each other and both of them are like very large errors, so we see that our model is not performing well and we want to like improve the complexity of the model. So if the two curves are very far from each other, then it's a sign of overfitting. So in this case, our training curve will have like a very low error, but our testing curve will have, our validation curve will like have a very high error. Okay. And in case of a learning curve, if the curves converge, adding new data won't help. And you might want to consider like changing the complexity or increasing the complexity of the model. Because the amount of complexity you have currently, that can only go so far. So you might want to do some kind of polynomial features or something like that. Now, if the curves have not converged, where is this? This is where the curve is converging, and this is where the curves are not converging, then adding more data will help. So yeah, so that those are like the conclusions where that you can actually get from the learning curves. This might not be a good explanation, but I encourage you to like definitely go through all the learning curves and the um, validation curves for like more in-depth understanding. I'll probably also like maybe post a link on the Slack for more explanation. Okay, so now I'm gonna go to the questions.
I don't think we have any questions, but oh, thank you, Rohan, your team, to give us a very nice lecture, and appreciate your time and contribution.
Hey,
So maybe I just ask the audience, do you have any questions? This is your time to ask for our two lectures.
Do you advise any testing method for make sure we got a good model?
any testing method for a good model?
Yeah, I mean, like to make sure that we are on the right path on to test the model.
Yeah, so in my research, what I use are primarily two things. One's Monte Carlo nested cross-validation,
Okay.
and the other is the permutation test. So the permutation test is nothing but um, a way of dismantling the relation between the input and the output and running the same cross-validation framework on that data. So how it works. Initially, you have the data, input data, and the labels, which are like correctly matched. So the first sample, let's say, is 1, second sample is 0, third sample is 0, and so on and so forth. And you run the framework, you get some results, you're good. You maybe do like a t-test from statistics and get some p-value, you're okay, fine. Now, in case of the permutation test, what you do is you permute the labels. So just randomly shuffle the labels, and now you don't have the correct matching between the input and the output. So now you have like an incorrectly matched. So initially the first sample was set to 1, now it might be set to 0 or something like that. And if you run the same framework again, if it's like a binary classification problem, the expected accuracy will be 50% because there is no relation. So it's like totally random. And for a binary classification problem, the random accuracy, random chance is 50%, so you will get a 50% accuracy. Now what you do is you run the t-test on this again, the student's t-test. And then you will see like for the p-value, you have like very high p-value, which tells you that the results are not significant when you run the permutation test. So that's one of the methods that I currently use, and I think it's a pretty robust method. So you can also use for like your machine learning problem.
So is the AUC would be random as well, like 50%?
Sorry, what? The AUC?
Yeah.
Yeah, in this case, yeah, sure, yeah,
Okay.
because the classification is a binary classification, so it's 50%.
No, I mean the cross validation. When you do the cross validation.
Yeah, for the cross validation, it's just calculating the scores on the test data. So yeah, 50% in case of a binary classification.
Okay, thanks, Juan. Appreciate it.
Yeah, cool.
Any other questions? If no, we're going to conclude this week's lecture. And I would like to thank Rohan again and your team to give us a very complete lecture on linear models. And I have also posted the assignment in the chat. And please go through the assignment, especially on the logistic regression part, and post any questions in the Slack channel, and also we'll discuss those questions during the week so that we can prepare ourselves for our next week's lecture. And so for next week, it'll be Team Gilbuson's team to give us a lecture on the decision trees and random forest. Thank you all for participating in today's lecture.